So we're back at it. So just to recap, this working for you guys? Because it's not working for me. Yeah, it's not letting me switch to the other class.
It's not? Maybe because are you on the right screen?
Probably not.
There you go.
No, thanks. Subject's so amazing. Okay, guys. So we have, what did we do here? Someone raise their hand and explain what this is.
It's like for the motive.
Yes, what is it doing though? What is it assigning? What is it creating?
Isn't it like a thing about a boat to look at?
Oh, something else. Ryan.
Making 4 new objects, 4 new Victor objects, and giving them numbers
Yes.
to identify them.
Exactly.
Yep. So if we think about the difference between a class and an object, there is one singular class called Victor SPX, and we are creating 4 instances of that class. Each of those instances is called an object. So one recipe for how this motor is created, what it does, and everything like that, and we now have 4 of them.
Okay. So after this, our next step is to. Are you good? Okay. So we have our motors, but is there any other hardware that we, Keegan?
The gyro.
Yes, we had to initialize the gyro. Okay. Can anyone guess what our access will be for this? Yep. So write private, and it'll be final because it's unchanging. And the type for this will be.
None of you are probably going to get this, so I'm just going to say it. And even then, I'm probably going to get it wrong. I think it's like an ADXRS.
Sorry, what was it?
I think it's an ADXRS 450 underscore gyro.
ADSRX. Oh,
450 gyro.
ADXRS
there we go.
450 gyro.
Yeah.
Look at that, I remember.
Okay. And what do we want to call this?
Our gyro.
Yes. So it's going to be equals to like this. Okay. And why don't we have anything in the parentheses right here? Yeah.
Yep, when they made the recipe for here's how you create a new gyro, they said we don't need to know anything else.
Okay. So right here, we have our motors. We initialize them. Motors, and then we also have created gyro. Okay, so we have all of our variables assigned here, and we have all of our hardware. So now our next step.
Do we all remember the question that we started with when we created this file? Do we need a constructor?
Mhm.
What do we think the answer is? We created all of our objects. We instantiated all of our objects. Do we need a constructor? I see Ryan shaking his head. I see Wyatt shaking his head yes.
Who's right? Let's take a vote. Who thinks we needed a constructor? Raise your hand. Okay, now raise your hand if you think we don't need a constructor. Oh my gosh, guys. Do you want to explain, Colin?
Yeah. So one thing that we don't have to deal with too much with our sim classes that we do have to deal with our hardware classes is there might be some additional configuration that we need to do after we've created the object. So for example, our Victor SPXs, we've created 4 of them, we've plugged them into 4 different ports. I want to think about a situation here where, say we tell the robot to drive forward. What that means is all of our wheels need to spin forward, right? So if I've got one motor that's on the, let's say this is the left side of the robot, and I tell it to spin forward, it's going to go like this, right?
We go clockwise.
Yep. And my wheel on the right side of the robot,
So it's clockwise. Like this.
yeah.
Yeah.
Yeah, I think I got it. They're spinning the opposite direction. Because if we take this one, the one that's going forward here, and we put it on the right side, it's not going backward. So what that means is we need to be able to tell our Victor SPXs, hey, some of you might need to be inverted. We might need to tell our gyro, hey, when, after we've initialized, reset and say, hey, this is your 0 point. So we do need a constructor because we need to be able to configure additional things like this. So let's make one.
Okay. Does anyone know how to create a constructor? Ryan?
Public, would it be public drive IO Victor SPX?
Yes, exactly. So to create a constructor, you would do public, then it would be the name of the class. In this case, it's drive IO Victor SPX. Then we would do parentheses and then curly braces. And this is our syntax for a constructor. So
The function, but the function doesn't have a return type.
exactly. So do we need any parameters for our constructor? Do we need any arguments or any parameters?
7. Why?
Arbitrary number. In the interest of time, I'll just say.
Yeah.
No, we don't.
Perfect. Okay, so now we can initialize these. We're going to want to invert some of them, right?
Yeah.
What side do you want to invert? It doesn't really matter.
Right side.
Right side? Okay, so to do that,
We have our objects. They're stored inside these variables. If there are methods that we want to call on the objects, the way that we'll do that is we'll say the name of the variable dot and then the name of the method on that object we call. So in this case here, that would be, say we want to invert our right motors. So this would be, say, underscore FR motor dot.
Destroy.
No, we don't want destroy object.
Aw.
Set inverted.
And why?
Boolean. So we want the one that does Boolean. And so we will say true if we want it to be inverted or false if we don't want it to be inverted.
We generally have this default is false, so we have that set to false. If it's
We'll start with that for right now. I don't think there's anything with the gyro. Okay. The next thing is, do we remember all those methods that we made in the drive.io interface? We now need to implement each of those inside this class. So we'll do that. I think we're done with the constructor. We'll go down.
so if we go back here, just to remind ourselves, we don't have to do the update inputs, right?
We do need to do that one.
Okay, we do.
We'll do that one last time.
Yeah. So first we'll go with the easy ones. We'll do power left and power right. So for power left, we can instantiate these here. So we're gonna call it's gonna be public. Yeah. Do we need an indentation for this?
Worry about that after you get back.
Okay. So it's gonna be public. Let me call it here. Do we need a default?
You don't need the word default.
But we do need a return type. No.
Yes.
Yes. Okay. Anyways, guys, I need to lock in here. Okay. What data
The
type?
easiest thing to do is probably just going to be to copy and paste what you have there and then remove the word default.
You're right.
oh,
Okay. So we can delete the word default because it's no longer in the interface. So we're over here now. Okay. And now we have our power left, double right. And now we have to actually do some stuff with these, right? We're not just creating them, we're actually going to use them. So can anyone think of how we could power our left side and power our right side?
What does it mean power the left side? We're telling the motors to do something. How do we tell the motor to do something?
Set them equal to.
What do I need to write on the screen in order to
let something do something.
What equals, so take a look at lines 21 and 22 up on the screen here. Here, we're telling our motors to be inverted.
So we should tell them to have receive power.
Yes. So we'll do this the exact same sort of way. We'll say underscore, let's see, we're on the left side, underscore FL motor dot, and then there's some function we need to call to tell it to drive with that speed. Is there a
Set?
set volt?
Yeah. I don't see it.
Oh, that's probably wants a Victor SPX. That's fine, we'll do that.
I guess it's that voltage.
Yeah, we were trying that. It's not working. Just do this.
SP words. I don't know if we have SPXs or SPs.
We are in Victor SPs. I gave you the complete wrong. Yeah, okay. Quick side note, Victor SPXs are CAN devices. We're working with Victor SPs, which are not CAN.
Motor controllers.
Up at the top, when we created our 4 motors, we called them Victor SPXs. Get rid of the X at the end of the type.
And we also want to get rid of the X at the end of our class name. And everywhere else. Pretty much that.
Yeah.
Good one. So, yeah.
And then it'll probably give these red squiggly lines. So when you give that, you're going to go hover over it. And you're going to go over to something called Quick Fix. Click on that, and you're going to do the top thing. It's going to say Import Victor SP. You're going to click on that. And also is going to say, yeah. So that should fix it. And if you go,
How do I?
so it should look something like this when you're done.
So you got the SPs.
I think it's this right.
Delete that whole line right there. And then if you hover over. There we go.
Did you change the name of the file to drive by on Victor SP?
Yeah, we should probably do that.
It's loading.
You'll need to change the name and then change the name of the file to Victor. Oh, yes, sorry, you will need to change the name of the file. I forgot that Java requires that your class name matches your file name. No, I work with C#. C# doesn't count. Most languages don't care. Well, it cares about syntax, it just doesn't care about it for something that doesn't matter.
Where is rename?
If you control, so you're going to go.
It's gonna give all the error codes that you find. Why am I getting 6 errors?
This is
Okay.
a little bit different because what we imported comes from the WPI.
Oh, yeah.
And then
Now it has only one recommended error.
the red squiggles. So there are other libraries that we could use aside from the WPI library. Victor SPX comes directly from CTRE. The Victor SP comes from the WPI library.
Several months expired.
Yeah, I had some of those. They were awful.
Everybody in March.
Okay, I think we're all caught up on that.
Okay.
You have to month expired.
So we're gonna go into the power left or power right, whichever you did first. And now we're gonna set the voltage of these motors. So we have to call our variable that we want to set. So we're on the left side, so we're gonna do front, right motor, or back. Yep. Thank you. Then we're gonna do set volts. So we're gonna do the dot, which allows us to set a method and access all the methods and stuff. And there should be a set voltage right here. So you're gonna click on that, and it should come up with this. And why is this giving an error right here? Does anyone know?
Joshua.
We need to give an input.
Yes.
Exactly.
Yes, exactly. Because it in the method when they created it, they wanted volts as the argument here. So one thing we have as our parameter right here, you can see is volts. So we can just insert that right here, and the error goes away. Does that make sense to everyone? So to recap, we're creating our variable, then we're setting our voltage, we're calling the method, and we're giving it the volts parameter argument. Okay, so now we have to do the same exact thing, but for the back left side. Okay, set voltage. Yeah, you're right. Set
Programming in
voltage.
front of a group is one of the hardest things you can ever do.
You're right.
Typing skills are out the window.
Yeah, it is scientifically proven that the more people you have watching you try to write code, the worse your code.
What typing?
That's what we're doing.
I work with some professional engineers who write code every day, and this is true for us as well. We
You write
forget
code
how
in front of people?
we forget how to write code in front of people.
Okay. Does anyone have any questions about this? Okay, so that we're gonna do the same exact thing, but for the right side. So we're gonna do front right motor dot set voltage and volts. Back right motor.
Yeah, if you have this typo.
Okay.
If you like working,
So- I'll give back.
All right.
Okay, is everyone good to go on this?
Yeah.
Okay, so we have these two methods are used, and now we have to reset our gyro. So we have our gyro method. We can copy that into here, and we can delete the default like last time. Oops, not that. So we have to actually copy it. So we can just copy and paste that because we're using the outline we already created. Okay.
Why do we have to re-input the, are these essentially constructors or are they just reinitialize? Why do we have to copy paste these over?
Because in interface, we have said these are functions that exist. And here we're saying these are how we're implementing them. So normally.
So this is technically a function call.
It is a function that exists.
So it just means that you have to bring them over so that you can use them from the second. Can you also use them from directly?
Okay. Are we good on this, guys? Give me a thumbs up if you're good to move on. Okay.
I'm going to say no.
So we have this reset gyro method, and we want to reset the gyro, obviously, when we click a button. So we'll connect this to a button later on. So how do we think we could do this? Yeah, Keegan.
Could we change the angle variable to 0?
So the angle variable is one of our inputs, right? And that variable is meant to represent the actual reading of the gyro itself. In this reset gyro function, we're not trying to read the input, we're trying to tell the gyro, hey, set this as your new 0, 1, 9.
So is it there like a set method that we could use like dot set angle or something?
Let's find out.
Okay, so we would type the variable first in order to access its methods. So we're going to take the method we created, not the method, the variable we created is up here. So we're going to write that. We're going to write gyro dot to access the methods, and we can look through here.
I think it's reset.
Yes, so reset. We push this, it gives us here, and we can hover over it, and it tells us resets the gyro. So there's some methods that WPILib already has built in and stuff and makes our life a whole lot easier. So you can look at documentation to find that. You can scroll through the methods, but in this case, all we have to do is call the reset method. And when this method is called, it'll reset the gyro. Does that make sense to everyone?
Yes.
Perfect. Okay. Okay.
All right, last method, update inputs.
This is a bit harder. Yeah, do you want to explain it?
What's-
Do you want to explain it, Colin?
Sure. So just like our other methods here, we're gonna have to copy this in from the interface. And what we need to do in here is we need to, get rid of the word default. Don't need the word default there. But what we do need to add in here is, so inputs. This has all of those variables that we added in earlier, right? So this is the FL motor speed, FR motor speed, and then the other two, and then the robot angle, I think was what we call the other one. We're going to want to assign values to all of those inputs so that the rest of the subsystem can read those inputs and work with them later. So let's start with the gyro angle because that one's going to be the easiest one. So if we want to get information out of our actual gyro, how do we think we do that? There's a method we can call. And how do we call a method on an object?
Dot.
With the dot. So we want to ask our gyro,
This angle?
I do believe it is gyro.getAngle, yep.
Mhm.
So the return of this function here gives us the angle that the robot is currently facing. And we need to put that into the robot angle variable of our inputs parameter. So what we'll say here is inputs dot robot angle equals gyro.getAngle.
And the inputs is what allows us to access this that we created back here. That makes sense? Kind of like the underscore kind of in a way, like with our member variables, but inputs allow us to come back here, read this robot angle, and then we can assign it to this and give it actual value instead of 0. That makes sense.
Let's stay here for just a second and get we're catching up. Okay. So this is how we assign one of our inputs. We've got 4 others we need to do, right?
Mhm.
So it's going to look remarkably similar to this. So we start by saying inputs dot and then whatever input we want to fill in.
And then we can, if you guys want to check, you can always go back and see, okay, we call it FL wheel speed. And then that'll be equal to, then we can get our wheel speed here. So then, does anyone, so this is the variable created. It doesn't have a value, right? But we have to assign it actual hardware in order to interact and be able to get it, right? So we can go back up here with the corresponding thing and do FL motor, and we're trying to find the speed of it, right? So we can do FL motor dot to call the methods. And what do we think we would use here?
Get forward.
I don't know if there's a get voltage. We can just say get.
And if you ever want to know what it means, you can always hover over it. Yeah. Okay, and now we're going to do the exact same thing with the other 3. So we're going to do inputs dot FBL wheel speed equals BL motor dot get inputs FR wheel speed. Motor dot get.
You have an extra P in inputs.
Thank you. Inputs dot
So this to run the actual robot?
Does this make sense to everyone? Okay. Well, we'll give you a little bit to catch up, but
So does everyone understand what is going on in this update inputs function? If you do understand, please nod. If you don't understand, don't nod. Don't lie to me. I'll know. I won't know.
Okay. So we have these update inputs. What do you want to talk about annotating?
Yes. So the very, very last thing that we need to do is each of these functions that we have put inside the class here, we are, so in the interface, we created these methods first, and they were all marked as default, right? That's saying if I have a drive IO object of any type, and drive IO Victor SP is a drive IO, if I call the update inputs method or the power left method, by default, I'm going to get the function implementation from the interface. Eden, can you go back to the drive IO class? That means if I have a drive IO Victor SP and I call the update inputs method, I'm going to actually call this update inputs method, which doesn't do anything because there's nothing inside the curly braces there. So we need to tell Java, hey, if someone has a Victor IO SP, or sorry, drive IO Victor SP, and they call the update inputs method, I want them to use the version that I wrote inside this class that actually does something, not the default method that doesn't do anything. And the way that we do that is right above the function name here, we add this thing called an annotation. So the way we do this is we type @ and then we type the word override. And so we'll need to do this for all 4 of the methods that we added in here. So it's just @ override above each of these methods. All right.
Is everyone good on that?
So override is when you need to call this instead of. So why do you have to make it in drive IO?
Because
Yeah, so drive IO itself is an interface, not a class. In an interface, you define all of the methods that anything that implements that interface can have, but you're not saying this is how to actually do it.
Okay.
So all of these methods that we've implemented, the power left, power right, reset gyro, those methods, we gave them one implementation here for our hardware class. If we created our sim class, there would be a different implementation.
And it's all because it's interfacing with drive IO.
Right.
Okay. So okay. So should we do a quick overview of this class?
Yes.
Okay. So who wants to tell me what this part does? Actually, this.
Even before that, let's start on line 6.
Okay. What is this line? What does it do? You.
It says that this new class is called Drive IO Victor SP.
Mhm.
It's gonna have like everything that's contained within Drive IO.
Exactly. So now we can go down. What do these 4 lines do? Should we go in around in a circle?
Yeah, I think so.
Okay, Ethan, what do these 4 lines do?
That's what
It assigns the motors 2 different ports.
Yes, exactly.
It initializes the gyro.
Mhm. Okay. What is this?
makes a function, or it makes a method for drive
Mhm.
IO.
Wait, hold on here. That's not a method. It's okay if I know you know better. This is the constructor. So it's not a normal method, but this is when someone wants to create an instance of a drive IO Victor SP, this is what has to happen in order to do that.
Works the right motors.
Exactly. Okay. So now going down,
We'll skip that overall.
Okay. What is this?
It updates the speed of the wheel.
Yeah, it updates the methods or inputs that we created earlier. Yeah, just like the title says. Okay, what do these four do?
They get the voltage for each hour.
And they assign it to the inputs. Yeah. And what does this do?
Does it reset the gyro?
Close. It gets the angle of the gyro and assigns it to our inputs. So really close. Okay. Ryan,
Yes.
what does this do?
That sets the well, it sets up the power left method so that when you call it, it'll set the two motors voltage to whatever you give it.
And what? What do these answer?
And try that. That part is like what the voltage is and voltage.
Yeah, setting the voltage exactly. And what does this method do overall, Egan?
Overall, that sets the voltages for both of the right motors.
Exactly what happened with over here, or with the right. And what does this method do overall, Ethan?
Overall, that method resets the gyro.
Exactly. Good job, everyone. Give yourself a round of applause. You did it. Okay.
All right. Everything that we've done so far has been specifically to tell our robot how to interact with the low-level hardware. We need to actually write a control algorithm that will take driver input and actually move the wheels the way that we want it to. So that logic is contained within the subsystem, and I think we should work on that next.
I agree. Okay, so we have these two files. So now we're going to create a new class like we have earlier. So we're going to right-click subsystems. And we're going to go down to create new class command. Huh? Yeah. So it should be called, if you scroll down on this list, you'll go down to the bottom and it'll be something called subsystem. We're going to click on this and we're going to call this, what do we think we would call this, guys? It's not a hard question.
Drive.
Yes. So we're going to call this drive and we'll push enter and then it'll go build something like this. You can delete that comment, delete the comments, fix the spacing. Okay. And when you guys are done with this, let us know. Or actually, give me a thumbs up if you're done, whenever you're done. Okay. Give me a thumbs up if you're done with this step. Do we need help with anything? Okay, give me a thumbs up if you're done with this step. Okay. Okay, we good? Okay. So, we have our subsystem here. One thing to note is that it extends subsystem base. So subsystem base is, if you hover over it, it's like a base subsystem provided by WPILib that all of your subsystems will extend is essential for like your subsystem class and stuff. So yeah, that's just important to note. We also have a constructor here, and we also have a periodic method that we mentioned yesterday. Does anyone remember what a periodic method is or what it does? Keegan.
I'm not sure. Is it the one that like runs every time? Like the robots refresh? Like
Every cycle. And how much time is within one cycle?
20 milliseconds?
Yes, exactly. So this runs every 20 milliseconds. You guys got it. Okay. So what would be okay. So the first thing we're going to create here is our updates inputs class. So something kind of similar to this. Location wise, we're going to put it below the constructor so you guys can kind of just like, we need to delete out the stuff in the middle.
We need to call the function inside the periodic inside the subsystem, but in order to do that, we need our drive IO inputs. We need to create a drive IO input and go back to the subsystem.
Okay.
So, in order to interact with our inputs, there's two things that we need. The first thing is we need to actually have a reference to our inputs variable. And so what we're going to do is we're going to tell the drive base, hey, create your own initialized inputs, and then whenever I tell you to update your inputs, I want you to update the version that you're holding on to. So the way that we're going to do this is we're going to start by creating a variable inside the class, and this variable is going to be called it'll be a private variable. So private, and then in order to update our inputs, we need an IO variable in the first place. So we can't just call update inputs on like an inputs object. We need to have a drive IO object. So what we can say here is our subsystem is going to be holding on to a drive IO object, so private drive IO. And we'll call this variable _IO. The other thing that we need is we also need our inputs variable. So this will be a private drive IO inputs. And we specifically want this drive IO inputs auto-logged. Sorry.
Oh, my bad.
Drive IO inputs auto-logged. Now, you might not have that drive IO inputs auto-logged type, and it might not recommend it. For right now, that's okay. Go ahead and type it out how it is. If there's red squiggles, leave those there for right now. And we'll call this _inputs. And then for the input specifically, we can say equals new drive IO inputs auto-logged. Okay. Does everyone? All right. Does everyone have this written? You might have an error, but is it written? Okay. Who has an error on drive IO inputs auto-logged? Got one? Two? Did that actually result for you guys?
I
Also,
Oh.
I don't think the thing, mine is kind of weird, doesn't really
Since
make
he's
sense.
on
Errors
Chromebook,
are much.
yeah,
Oh.
it doesn't show him errors on Chromebook, and it also doesn't like give him that like pop-up of possible options.
Well, just don't make mistakes and then you'll be fine.
That's crazy.
Okay. So I want to explain super quick what this drive IO inputs auto-logged actually is. Eden, can you go back to the drive IO interface?
Mhm.
So in Drive.io, we created this static class called Drive.io inputs. And we added an annotation above that for @autolog. All right, I feel like there's a lot of conversations going on here. Am I losing people? Are we following what's going on? Okay. So this @autolog annotation, what this does is it tells your program, hey, when you build me to put me on a robot, what I want you to do is I want you to take Drive.io inputs, and I want you to create a new class called Drive.io inputs autologged, and that's going to have all of my inputs plus some extra stuff that AdvantageKit does to actually log all of that information. So if you don't have this Drive.io inputs autologged class, it's because we haven't built yet. So we don't have, that class doesn't exist yet. We'll leave that for right now. So for these two variables, Drive.io and then Drive.io inputs autologged, we're initializing one of them, but not the other. So IO, we're going to initialize inside the constructor. And the way that we're going to do this is when you create an instance of Drive, you need to give us a Drive.io object to use. So we're going to need a parameter for our constructor. So the Drive.io, and we'll call it IO. And then inside the constructor, we can say underscore IO equals IO. So this might look a little bit weird, but what's happening here is when we create our Drive subsystem, we need to tell our Drive subsystem, hey, here's the hardware you're working with. So in most cases, we will want to give this our Drive.io Victor SP class. But when we're simulating, we won't want to give it a Drive.io Victor SP because that deals with hardware. We'll want to give it a Drive.io Victor or Drive.io Sim, which we haven't created yet, if we want to simulate the inputs. The subsystem doesn't care. It'll run the same logic regardless of what kind of hardware it thinks it's interacting with. It just needs to have a reference to what it's actually going to be interacting with. All right. So with these two variables defined at the top and our Drive.io passed in through the constructor, the next thing that we're going to do is we're going to go down into the periodic method. And like we said earlier, this periodic method runs every 20 milliseconds while the robot is running. And every 20 milliseconds, we want to update our inputs. We want to read whatever our new values are from our motors and from the gyro. How do we think we can update our inputs?
Drive.io Victor SP dot update inputs.
You're very close. We don't have a Drive.io Victor SP in here, but we do have a Drive.io. And that also has an update inputs method, so we can call that one. So what we'll say here is underscore IO dot update inputs. And we'll pass in underscore inputs. All right. And that's how we read our inputs every 20 milliseconds. All right. Now, the next thing that we need to do, and actually the last thing that we need to do for the subsystem, is I mentioned that we need to be able to take our driver's joystick input, and we need to be able to convert that into voltages for our left and right motors. So we need to write some sort of control algorithm to actually do that. How do we want to do that? So I know that's a super big question. We're going to write a method because we have a sequence that needs to happen. We need a method to do that. So let's go down under the constructor. And this method is what we're going to call when we want to drive the robot. So what should we call this method?
Drive.
I love it. What do we need before the function name?
Publish.
Public
Void.
and void. Yep. Drive. All right. Now, when we are driving, how does the robot know how to drive? We're getting our joystick input, right? But what input specifically are we getting from our joystick? A percentage of what?
Think about
Vector
math.
input.
X and Y. Yep, X and Y is right. So our joystick, I'm gonna air joystick here. Our joystick has two axes. It's got an X axis, which is left and right, and it's got a Y axis, which is forward and back. So if we think super quickly about what that input does, what happens if I press all the way forward on the joystick?
Y goes all the way up.
Y goes all the way up. What does the robot do?
Sets voltage.
It sets voltage to max in the forward direction. And if I go all the way back,
It sets Y to
Max in
zero.
reverse.
perfect. And then what happens if I go all the way to the left?
Turns them.
Goes all the way to the left.
Voltage to max in opposite directions that makes the robot turn to the left, right? And then the opposite's true if I go all the way to the right. So what it's sounding to me like is we have two inputs. We have our drive, which is our forward to back, and we've got our rotate, which is our left to right. Now, our joysticks give us those values in a range of -1 to 1. What that means is -1 is full power backwards. You can think of it as -100%, whereas 1 is full power forwards. And this is true for both our drive and our rotate. So what that means is we're going to take in two parameters here. One is our drive input. One is our rotate input. If those numbers are represented in the range of -1 to 1 as like percentages, what data type do we think we need? Double.
Double X and double Y.
Let's call them double drive and double rotate.
They look like trees.
Okay, so drive and rotate. We get our joystick input. Now we need to convert that into a left speed and a right speed. And this is the part where I draw on the board.
Math.
There is going to be math involved, yes.
All right, so I'm gonna draw a robot here, and this robot's got wheels on the left. It's got wheels on the right.
It goes on its back. It goes on its front.
It doesn't have wheels on the back or front, unless you are counting this as the back and the front. Okay. So, if I'm pressing all the way forward on the joystick, what directions are our left wheels and right wheels turning? Let's start with the left wheels. If I'm pressing all the way forward, let's say forward is this direction on the robot. Clockwise from one side, but counterclockwise from the other, right? To make it simple, I'm just going to think about it top down. We want the left wheels, if I'm going forward, I want them to go forward, right? Right side, if I'm going forward, we want those to go forward. Forward. All right. So that's the drive component. If we just want to tell our robot to drive forward and backward and not worry about rotating, this is enough right there. We could take our joystick input and we could multiply that by 12 to go from a percentage to a voltage, and we could pass that on to our subsystem, our drive IO, and everything would be all perfect. But we want to make it so our robot can rotate, right? So now say I'm going all the way to the right. What direction are my left wheels rotating? Forward. If I'm rotating to the right, that means my left side has to be going faster than my right side, right?
Yeah, so forward.
So the left side needs to go forward, and the right side
Just go backwards.
needs to go backwards.
You play enough racing games to know this.
What's that?
Played enough racing games to know this.
Perfect.
Okay.
So it's the same.
So what we can do here is we can just take these two components, our drive and our rotate, and we can add them together. So what we can say is our left side, and I'm going to abbreviate here. I'm going to say L, that's an L, is equal to, because they're both going the same direction, we can say it's drive plus rotate. Our right side, this is a different R from this R. They are not the same thing, so don't get confused by that.
R.
They're not the same. The right side is going to be equal to, so drive is our positive one. Say drive minus rotate. And again, these R's are different.
Just make the R uppercase.
Yeah, that's a good idea. Let's do that.
It's a big variable, so just make it uppercase.
That's what I'm saying.
All
I
right.
didn't. I said that.
Speak louder.
Yeah, I'm sorry if you said that. I didn't hear you. Okay. So we have left is equal to our drive plus our rotate. Right is equal to our drive minus our rotate. Now, remember that I said the percentages are given in the range of -1 to 1, right? Now, for something like drive minus rotate, if I'm trying to drive full forward and rotate full to the right, that means my right wheels are going to do, 100% minus 100%. My right wheels aren't going to move, right? But my left side, I'm going to say we're driving at 100%. We're adding another 100%. I can't tell my motor to drive at 200%, right?
It's just 50-50. 50-50.
Well, 50-50 on both means that it's going to drive forward at half speed, right?
Drive forward at 50 plus 50, that's 100%.
What's that?
On our side, 50 minus 50 is 0.
So 100 and -100 is going to make it rotate in place. But if we're driving full forward and rotating full to the right, what we really want to see, what's going to happen in practice is we're going to essentially be rotating around the point between those two wheels. So the right wheels are going to stay still and the left wheels need to be on at full power.
So give the drive a slightly higher percentage of the power, so it's always driving forward.
You're on the right track.
Are you able to cap the value?
We are. And specifically the important part is we need to make sure the ratio of the two sides stays the same. We want our maximum value to always be at most 100%. But the important thing is that the ratios between the two sides are the same. So in this case, I've got 200% and 0%. If I cap one of those at 100% to keep the ratios the same between them, what do I end up with? 0 scaled by anything, 0 times anything is 0, so the right side is still going to be stationary, right? But if I scale 200% down to be a maximum of 100%, what does that end up being?
100%.
100%, perfect. That's the easy case. Let's say, I'm not going to do the math to figure out what the drive and rotate I need for this is, but let's say my left side is 200% and my right side is 100%. If I need to scale those both down so that I have a maximum of 100% but keep the same ratio between the two, what numbers do I end up having?
33, 33, and then 33 divided by 2. Other side.
Sorry, they can both individually be up to 100%, so they don't need to add up to 100. So you don't need 2/3 and 1/3. We can go full speed on one side. So if I have 200 on one side, 100 on the other, that means my left side is going twice the speed of my right side. So if I scale this from 200 down to 100, it still needs to be going twice the speed of my right side, right?
It'd be 150.
100 on the left and 50 on the right. That's exactly right. Okay, we've talked about some examples. Let's actually turn that into code. So what we need to do is we need to figure out 4 minutes. All right. We'll go as fast as we can here. All right. So we only need to perform this scaling if one of these numbers is above 100%. So the first thing that we're going to do is we're going to find what our maximum speed is. And then if that maximum speed is greater than 100%, or less than negative 100%, because the direction also doesn't matter in this case. What we need to do is we need to divide the left side and the right side by that maximum speed. So, what this means is, let's say our left side is 100% and our right, let's say our left side is 200%. And our right side is 100%. We need to take whichever one of these is bigger. In this case, it's 200. We need to divide both of them by whichever one is bigger. And when we do this,
1 and 0.5.
yep, exactly right. So that'll give us our
Or 0.5.
Our ratios.
0.25 or 0.25.
Yep.
0.
As far as what this code actually looks like, we are out of time for tonight. So I want you guys, before tomorrow, to think real hard about what this code's actually going to look like. And we'll handle this right away when we come back tomorrow. Does anyone have any quick questions before we officially end? All right. Great job tonight, everyone. Oh, that's
Yeah. Basically, all it says is L equals A plus R, R equals E plus R, A equals R for the second one. And then 200 over 200 equals 1. I talk really fast.
Yeah.
Basically, just
Hopefully the explanation I gave
make enough sense.
make enough sense to know what those numbers are.
Yeah, that should be it. And we'll stop recording.
It goes well.